All right, so like you can see, let's turn the light on. So the first thing we're going to cover today is a real short recap of using modulus in order to do conversions from one unit to another when the units are in the same general system, but you're doing like from cents to dollars and cents, or ounces from pounds to ounces, that kind of thing, because the homework is from pounds to tons, and so it'll be exactly the same kind of thing. So I have a note here that I published. From now on, I want screenshots as well as your code when you upload the code. Why? Because people are turning in stuff that doesn't run, and I want you to know that it doesn't run. I don't want you just uploading it and kind of hope that I don't notice that it's not going to run. So we'll talk about how to take screenshots. So assume that that's a requirement from now on, even if I don't modify all the documents to say that. Something else is it would be easier for me to grade on the Mac if we made a few changes to our coding conventions. So, if I can remember what they are. So when we're adding our boilerplate, I'd like for you to do this. Put your IO stream in it. Put your string in there, but also add one more. And if you don't do it, I'm not going to count off. It just is something that when I'm grading on the math, I have to go in. CMath. Why is that? Because if you're trying to use the POW function, it comes in by default on Microsoft Visual Studio, but it doesn't come in by default on Xcode. If you include that, then it's more proper. Microsoft's is kind of at a, they're at odds with the rest of the world in not requiring you to use CMath in order to get the math functions. So I'd like for y'all to do that. I'll post this as a note. The other thing is, from now on, let's declare main as an int rather than a void. That's more strictly correct. Again, Microsoft should not be allowing us to declare main as void. What does that do? This just means a return type. It's going to return a value. So instead of just doing return, we're going to do return 0. We're just making our programs a little bit more standard compliant by doing these things. So what we did, what we studied, was using modulus. And what we know what modulus means. It means remainder of. So if we do this, don't type this into code. X is equal to 99. And then y is equal to x modulus 10. Can I find the percent sign? That means 10 goes into 99 how many times? It goes in 9 with a remainder of, come on guys, 9, right? Yeah, so y would equal 9 at that point. What if we did y is equal to x modulus 30? How many times does 30 go into 99? 3 with a remainder of, again, with a remainder of 9. What if we do y is equal to x mod 5? I'm not trying to pick hard ones, you know, x mod 17, yeah, whatever. Okay, so 5 goes into 99 like 20 or 19 times with a remainder of 4. Yeah, okay. So we know how that works. So you can use it to convert from one unit to another. So for example, if we ask them to type in convert centimeters to meters and centimeters. So we do this. We input into centimeters, and then we do meters is equal to centimeters divided by 100. And then we do centimeters is equal to centimeters mod 100. So let's go ahead and write that out completely. We'd want to see out how many centimeters. And I'm assuming that everybody here, most of y'all, were here. So you don't necessarily need to do this. And then we would need to declare centimeters and meters. So we CN into centimeters. We do those two calculations. So to convert to the larger unit, we divide. and then we catch the leftovers with modulus. And then we could do cout, that is, or meters equals, you know, followed by meters. And centimeters, cout. I know you can't see past my monitor. I'm sorry about that. Cout centimeters equals like that, centimeters. Now I'm not going to give you more examples because this is the exact way to solve the problem. How many pounds? Int, pounds, tons. Read into pounds. Tons is equal to pounds divided by 2,000. And then pounds is equal to pounds modulus 2,000, and then print your variables out. So it's a pretty easy assignment from that point. And I do apologize for losing the lecture. I can't always guarantee that the lecture will be there because sometimes the machine crashes. We've been having a good run of luck, but we had a problem on Thursday. So anyways, these are our new standards. You don't have to adhere to them, but I would appreciate it if you did. Of course, our boilerplate also includes pause, you know, or system pause, which doesn't do a darn thing for the Linux and the Mac users, but it's nice for us PC users. So that's our new boilerplate.
So we always put the return 0?
Yes, please. Yes, please. Yes, please. Yes, sir.
What does a return 0 do?
Good question. We're going to have to talk about functions in order to do that. To talk about functions, we actually want to go ahead and pop open Visual Studio and play. So create a new project called September 12. And yeah, the question was, what does that return 0 do? So September 12 is the name of my project. It's a C++ console app. No, it's an empty project. Going to add a new item, C++ file. I'm going to put all of my boilerplate into it. # include IO stream. # include. If you're not using strings, you don't have to # include string, but I just strongly recommend you do it as a matter of course. Because, I won't even talk about that until a minute. And then # include cmath in case we raise something to the power of something else. Maybe we'll make this do that. And then int main. Oh, I forgot that using namespace. std. One thing we should get away from is we should stop doing that. It makes typing easier. But the last thing we do before we submit something is actually comment that out and fix everything we have to comment, because that's professional. Professionals don't like doing this using namespace because it brings in a lot of things that you don't expect to have been brought in by doing that. So anyways, here we have our boilerplate, system pause. Everything is there now. You can write functions. Main is a function, but we're going to write another function. We're going to write a couple more functions, and this isn't part of the lecture, but y'all are going to need to know it eventually, so let's do it now. Let's make a function called say hello. And all it does is see out the word hello, ! \n. That's an example of a function. It doesn't return a value, so it doesn't need a return statement, a return 0, or anything like that. I forgot to put my return 0 down there, didn't I? I'm going to go add that. Who is blowing up my phone? So when we want to say hello, we just do say hello, like that. If we want to say hello twice, we do that twice. Say hello twice. Say hello 3 times. So we have kind of extended our programming language, and we have a new command. That's all a function is a new command. It's a new block of code that has a name. Now functions can accept input. We're going to write a better version of say hello, where we can make it say, hi Bob, or hello Olivia. So go ahead and compile this, make sure it works. Build, rebuild solution. Hello, hello, hello. Press any key to continue. All right, so it worked. Now we could put anything we wanted to in here. We could make it print out hello 20,000 times, and then each time we called say hello, it would print it out 20,000 times. I don't feel like doing that, but we could. Let's add another function called hi there. Void hi there, but inside the parentheses we're going to tack on something. We're going to type in string name. We're declaring a variable inside the parentheses of our function declaration. That's what's known as a parameter. It's a variable that accepts something when it's called. That looks like hit here. Hi underscore there. Now I'm happier about it. Okay, so now cout hi, comma, end quote, followed by a couple more arrows, followed by their name, followed by ENDL. And along with those say hellos, let's do a couple of hi there's. Hi underscore there. I'm going to scroll up. Sorry, guys. Hi there, Bob. And hi there, Carol. And it's okay if you don't totally get this yet. We haven't hit the chapter where we're talking about it. We're getting a sneak preview. When I ran it, it says, hi Bob, hi Carol, hello, hello, hello. So we have added a command, a function, so that anytime we want to say hi followed by a name, we just call hi there and we pass in the name as an argument, like that. And we did it again, but we passed in different data. So it said hi Bob, and then it said hi Carol. So these are functions that say hello and hi there are functions. These functions don't return anything. They're not returning any values. They're not performing any complex calculations. They're just doing something. It's like telling your little kid to go outside and take out the trash. He's not supposed to bring in anything back. So that's why these are declared as void. Void means nothing. They don't return anything. I'm going to pause and make sure that everybody's got this working before we talk about the next kind of function, which is one that does return. So now we're going to write a function that does return a value. And since it does return a value, we're not going to declare it as void. This is going to be a really dumb function, by the way, guys. Int I underscore am underscore 13. All this does is return 13. And so up here at the top of main, I'm going to do this. Int x, on the next line, x is equal to I underscore am underscore 13 in parentheses. And then I'm going to print out x. X equals, end quote, arrow, arrow, x, arrow, arrow, ENDL. When it runs, it's going to print out that x is in fact 13. So what it's doing, it's going sequentially. Int x, it's got a variable, x is equal to, oh, and it hits these parentheses, that means it's a function call. So it finds a function, I am 13, it hops up here. Now we're inside that function. Return 13. Okay, return means pass, like a football, passes back out of the function. So 13 comes back over here, crosses equal sign, and gets stored into x. So at that point, x is equal to 13. So that's what return does. Now, why we have to put a return statement at the end of main is because C programs and C++ programs are designed to run. They make executables, which you can invoke from scripts, from a bash script if you're a Linux user, or from a command file or a bat file, or things like that. And you can check the return code. You can write a script that'll run, and if it can't open a connection to another server to get some data, then that executable could return a -1, and your script can then print a warning message. Hey, we weren't able to run it. So main should always return a value, and it should always return a 0 unless it's in an error state. Now, do we run these things from scripts or from command prompts? No, we don't. So really, we ignore that, but it has to be there anyways to be industry standard. Let's write one more function called cube. And what it's going to do is it's going to take a value and then cube it, which means rate x times x times x. So int cube, and it needs to take a variable. I'm just going to call it x. And we're going to return, and I do want to use a math function, just use, that's Java, sorry, POW parentheses x to the power of 3. Can I move this so that's easier on you? I don't need this to be right in the path of everybody.
That's fine.
All right.
It'll work.
I'll work on moving it later. Okay. So down here, after we call x is equal to im13, we're going to add one more line of code after that x equals im13. Tack this on. X is equal to cube parentheses x. Now I think 13 times 13 is 169, so when this is done, it should print out 169. It didn't. It printed out 2197. Oh, because it's not just squared, it's cubed. All right. So what this is doing is we've already seen what happens when we say x is equal to im13. The code ran up here, ran this function, and it came back, it returned with a value of 13, which was copied into x. And then we call it x is equal to cube x. Now this is what's known as an argument. If you put something between the parentheses, it means I'm passing this into the function. So that 13 gets copied in to this variable x here. And then POW means to the power of. It's a function inside the CMath library. 13 to the power of 3 is 2000 whatever, and then it returns it. So the function returns, carrying back that value of 2000, which gets copied into x, and then we print it out. So that's a long explanation of what return does, but that's what it means. We invoke a function by calling it with its name, followed by parentheses, and if it requires any arguments, we put them inside the parentheses. It runs that named bit of code, which could be 1,000 lines of code. These are just one-line functions, but usually functions are longer than that, because if it's only one line of code, why would you put it in its own function? That doesn't save you anything. But if it's 100 lines, that's great, because you can call that function over and over just by using its name. You wouldn't have to rewrite that 100 lines of code every single time you wanted to do all that. And you can repeat function calls as often as you want. You can take those functions and bring them into another program, and they're already written. You can export those functions as a library so that they're easy to use inside of other C++ programs, or put them in a DLL. You may have heard of DLLs. Those are functions that have been put inside of a DLL library so that other executables can call them. Now that's a bit beyond what we're doing, but that's what a function is. We will be writing them soon enough. So the string class. What is a string? It's a collection of data between double quotes. An empty string is when you do that and there's nothing between the double quotes. Usually you don't have that. You might initialize it like that. So it's a special data type that supports working with strings. Now what's confusing is that C++ already has a string data type built into it. And it's a really lousy, bad one. So people immediately developed a better one called the string class. But they never took the old one out. And so if you don't add this word to this line to the top of your code, then it uses the old bad version of string. So we pretty much are going to be including this anytime we are working with words, with names and things like that. Do you need a string class if you're just, dealing with pure numbers? No. But if you're asking users to type in their name or, type in the inventory description and stuff like that, you are going to be using strings. So just out of habit, to prevent it from using that old bad version of string, I always add that in there. I was talking about boilerplate. Did I have any? Oh, yeah. Using namespace std. Okay. I'm going to save that and upload it as new boilerplate. So the string class. First name, last name. First name is equal to George. Last name is equal to Washington. So it's data just like any other kind of data, except it's not numeric data. Everything else we've talked about so far is numeric data. Even if it didn't look like numeric data, if it was a letter. We hadn't done the character data type, but I'm sure we hit a slide about it where you can say that character mychar is equal to, in single quote, k, end quote. Well, that k is really a number behind the scenes. But a string isn't just a number. It's a whole series of numbers that represent these letters. So here's a program, string movie title. We declare a string called movie title. We set the value of that variable to Wheels of Fury, and then we do cout. My favorite movie is Wheels of Fury, ENDL. Not really very much about the string class. You can use CIN to read into it. You can use COUT to display it. You have to be kind of careful about reading in strings, though. If you tell them to type in their name and they type in 2 words and you're only expecting 1, that can be a real problem. We'll get into that a lot more later. Floating point data types. Floats, doubles, and long doubles. They hold real numbers. They're just numbers with decimal points, with partial components. Inside the computer, they're stored in a form similar to scientific notation, where you have a so-called mantissa at the beginning and then you have an exponent value at the end. And they are signed. There's no such thing as an unsigned float or an unsigned double. You just use these for all the values that aren't going to be whole numbers. Use whole numbers if they use ints and longs if they are going to be whole numbers, because they're going to be more precise. I think I did a little lecture about that. Have I demonstrated the rounding error that you can get? Rounding error sound unfamiliar? Is that a yes we did or no we didn't?
We may have.
We're going to do it again. Alrighty. So here's an example of a rounding error. Go all the way down in your code to pause and do this. Float F1 is equal to 9.7. Float F2 is equal to 9.9. Now we're going to do a little bit of math on them. F1 equals F1 plus 0.1, or 0.1. That'll raise it to 9.8, right? F2 is equal to F2 minus 0.1. And then print those guys out. Cout F1 ENDL, and then cout F2 ENDL. Now they both say 9.8, but let's compare them and see if they actually are considered equal. If F1 is equal to F2, cout, they are the same. Now, I probably accidentally chose something that actually does not exhibit rounding errors, in which case we'll try something else. else C out, they are different, \n. They look the same, but it says they are different. There's an incredibly small difference between those two numbers according to the computer. And the reason for that is that although you can store whole numbers precisely in binary, you can't store decimal numbers, floating point numbers, precisely in binary. If you try to store 0.7 in binary, it winds up being an infinitely long repeating string of digits, just like if you divide 1 by 3, right? 1 divided by 3 is 0.333 out to the end of time. Well, same thing for storing them in binary. 0.7 in binary is an infinitely repeating series, and so is 0.9. So even though they look the same, they're not. We can find out what the difference is. Let's calculate the difference. Float diff, for difference, is equal to the absolute value of f1 minus f2. And let's print that out. C out, difference equals, end quote, arrow, arrow, diff, ENDL. Look how small that difference is between them. It's a decimal point followed by 6 zeros and then a 9. Very small difference, but there is a difference between the two.
How would you compensate for that? You actually,
Good question. Here's what you do. You compare the difference. If the difference is less than 0.0001, then print close enough. And they are. Whoopsie. Come back. So the difference is that, but they're close enough. You're just defining what is an acceptable difference there. Does it need to be, to 4 decimal places? Does it need to be to 6 decimal places? We saw that 7 wouldn't have worked, but 6 decimal places, that's 1/1,000,000th. That's probably pretty close. Close enough. The reason I'm going on about that is just to know that floating point numbers are not precise, or they may not be, just like 1/3 is equal to 0.333. Well, 0.333 is not exact, right? Because it's really 0.333 out to, an infinity number of digits. Same for floating point numbers, and you don't know which ones are going to be infinitely repeating like that and which ones aren't. So of our data types, we have floats, we have doubles, and we have long doubles. You can ignore the term long double. But what a float is it's got 32 bits in it, which is 32 divided by 8 is 4 bytes. A double is 64 bits, so it's a lot more precise. That's 8 bytes because 64 bits divided by 8 that's how many bytes. And then a long double is the same as a double. So why do we have it? I don't know. Forget it. And I just recommend using double throughout. It's more precise. Kind of like you could use long everywhere rather than int. But double is the default data type for numbers that you type in as decimal points into the code. If I type in this, don't type it, x is equal to 3.141159, the compiler treats that as a double. So I may as well use doubles to catch it, right? Double x is equal to 3.14159. If I didn't want to put it in a double, if I wanted to force it to be a float, I could do so by suffixing it, following it with an f. But why would I bother doing that? So rule of thumb, make all floating points doubles. Doesn't hurt anything, doesn't speed up the program if you make them floats. It makes it use it a bare handful more bytes. You get a lot more precision, much larger numbers. So here we go. Float is what's known as single precision. It's 4 bytes. So it can go from negative 3.4 exponent 38, so 3 followed by 38 zeros. The maximum value of a double precision, it's double wide, it's got 8 bytes, is a 1 followed by 308 zeros. You can see that that's a much larger value, right? And then a double precision is just the same as a double, so we don't need to care about it. So floating point literals. You can use the E to mean exponent if you want. If you want to say 3.14159 E1, which really would make it 31.4 if you're up on your scientific notation, you can do that. Or, yeah, what do you know? It was right there. So this is the same as that. This is the same as that. You can use uppercase E or lowercase e. Are you going to use E all the time? Nah, probably not. But if you need to enter like a scientific constant, there's something called Avogadro's number in chemistry. Avogadro's number. If I wanted to declare it as a constant, it's a floating point number, so I'd make it a double. I don't know how to spell Avogadro, so I'm going to leave it like that. Is equal to 6.022 exponent 23. That's the number of atoms in a mole, if you care, in chemistry. So would I want to type out 6022 followed by enough zeros to round it out? I could. I could have done const double. Avogadro's number is equal to 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. All right. Am I glad I did that? Nah. So the power of scientific notation, if you understand it, great. You can have constants, literals are double by default, as I mentioned. But if you want them to be a float, you can make them an F. If you want them to be a long double, which is stupid, why don't we edit all these slides and remove references to long doubles? I'd be happier. Don't need them. So here's their program. Distance is equal to 1.4 e to the 11. The sun is that many meters away. 14 followed by 10 zeros. The sun's mass is 1.9 e to the 30, or 19 followed by 29 zeros. That many kilograms. All right. It's just a variable, just like any other kind. I'd use double throughout. The Boole data type. Boole stands for Boolean. George Boole is a guy who invented a numbering system in scheme of logic where there were only 2 values, 0 and not 0. In other words, 0 or 1. Or in logical terms, true and false, where false was 0 and true is 1. So Boole represents values that are true or false. They're stored as a small integer, but who cares? False is a 0, true is a 1. But we're not going to say if something equals 0 or something is equal to 1. We're going to do if something equals true or something equals false. So Boolean, Boole, all done equals true. Boole, finished equals false. So then later on you could do if all done, print out a message. Or you could print if finished, print a message. And so you use these as so-called flags. A flag is something that indicates whether something is true or not, or something is false. Let's go in and see if we can come up with a reason to have a flag. How about this? You see that line that says if difference is less than blah, blah, blah? Comment those 2 lines out. We're going to make a variable called close enough. Boole, close. That's good, right? I'm not going to make us type in the words enough. And then close is equal to, parentheses, diff less than 0 point, and then 5 zeros followed by 1. 1, 2, 3, 4, 5, 1. Now we're ready to print out our message. If close, see out, arrow, arrow, close enough, exclamation mark, backslash n. So you see what we did here? We took this, but we changed its logic a little bit. We created a variable to hold the truthiness, as Colbert would have called it, of this statement. Is difference less than 0.0001? If it is, then store true into that variable, else store false. And then we can use that on if statements or while loops or whatever. If close, if it's close enough, print out close enough. So that's a Boolean variable. Boolean variable is one that's set to equal true or false, and you set it equal to an expression that returns true or false. A logical expression. Logical expressions are things like, is x equal to 3? Or is x less than y? You know, greater than, less than, equals, not equals. All of those are logical comparisons. Determining the size of a data type. This is the only language, unlike Python and Java and C++ and JavaScript and C#, that you'll ever, wait, I said C++. You're never going to use this in any other language. But sometimes it's useful to know how many bytes your data is occupying. We can use the word size of to find out. So let's just scroll down all the way to the bottom near our system pause. And we're going to do this. Int SD, for size of double, is equal to size of an int. And then int SL, I'm going to make it an uppercase L because otherwise it looks like a 1, is equal to size of a long. Why didn't I make that SD? That should have been the size SI, right? Because this is an int. Change that to int SI. Sorry about that. Now we're going to do two more sizes, a size of a double and a size of a float. So int SF, size of float, is equal to size of a float. And int SD is equal to size of a double. And let's just print all those things out one after the other. I don't even care if we put any text next to it. C out, SI, followed by a space, followed by SL, ENDL. It should have been a capital L. Figured that would come back to haunt me. And then let's print out the other two sizes as well. C out, arrow, arrow, SF, arrow, arrow, followed by a space, arrow, arrow, followed by SD, followed by ENDL. And here we go. We see that integers are 4, longs are 8 bytes wide, floats are 4 bytes wide, and doubles are 8 bytes wide. Do you personally care about this? Do you stay up late worrying about how wide an int versus a double is? No, but there are times when you need to know the length of it because you need to perform a calculation to figure out how long a data structure is. If you're writing some data to disk, you may need to know how many bytes it occupies so you can tell how many bytes get written out. And when you're using something called an array, which is a list, and you want to know how many items are in the list. If you use Python, it makes it real easy. There's a function, len, for telling you how many items are in a list. In this language, there's not. And you have to take the size of the array and divide it by the size of the elements of the array in order to get the length of the list. When we get to arrays, we will talk about that. So just memorize that size of returns the number of bytes occupied by that data. And you can pass it a variable type like that, or you could actually pass it a variable. I could do size of x, you know, if x was defined up there. I don't remember if I did. Size of name, if I had a string called name, that kind of stuff. Variable assignments and initialization. We've been doing this all along, so this slide ought to take 2 seconds. Once you declare your variable, you can give it a value. That's called an assignment. We use the so-called assignment operator, which is a single equal. We've talked about the difference between single equal and double equals. Double equals does a comparison. A single equal assigns, meaning copies across. So item is now equal to 12. The variable receiving the value must appear on the left side of the operator. If you do this, item is equal to 12. Looks good. In English, that'd be great, but in computerese, it's not good. The left-hand side has to be the value. The right-hand side has to be the, I got that reversed. The right-hand side is the value. The left-hand side is the variable. The right-hand side can be anything that you want, but the left-hand side has to be a variable. Else you can't copy anything into it. What would this mean? 5 is equal to 12. We're going to try to rewrite the laws of the universe so that we can stick a new number into 12? No, we can't do that. You know, A is equal to 12. Are we taking whatever is inside of A and putting it into 12? That doesn't work. So to get it right, you'd have to do A is equal to 12, and that would copy the value, assign the value of 12 into A. Initialization. Initialization is when you assign it right as you declare it. Int length equals 12. Do you have to do it like that? You could just do int length and then do length is equal to 12. It's 2 statements rather than 1. It's up to you how you want to do it. You can initialize more than one variable on the same line. Int length is equal to 12, width is equal to 5, and an area doesn't have any value at all. Now I'm already recommending that we don't put multiple variables on the same line. Why? Because we can give comments if we don't. You know, I could explain with a comment what this is if I put a semicolon here and did, you know, length of the whatever it is. And then int width is equal to 5. I'd put, you know, width of the whatever it is. And then lastly, int area, I'd put, you know, area of the whatever it is. Rectangles or something. This is my preferred style. I recommend that you adopt it. 1 variable per line. If you don't, that's okay. I'm not going to count you off too much. No, I'm kidding. I'm not going to count you off. So here we go. We declare 2 variables. Int month is equal to 2. Days is equal to 28. Print month, variable name, has, variable name, days. So when it runs, it says month 2 has 28 days. Have we been doing this? Yeah, already. Yeah, we have been. What we've typically been doing, though, is just putting 1 variable per line. Month equals month. Days equals days. But you can string up a whole bunch of prints if you want to. You can, I can't copy that, but you know, if you wanted to, cout si followed by a space, followed by sd, followed by some words. Don't type this. Something. You even want to go to the next line, that's cool. Gonna type a whole lot more. And then, yeah, you want to go to the next line. Let's put some /ns in there to go to, you know, the next line, so cause a line break, you know, and then whatever. You know, you get the idea. You can make a really long cout statement. Or you can just do what we have been doing. Print mass equals whatever, print length equals whatever. Whatever is appropriate for what you're trying to display to the user. Whatever you think looks better. I'm going to completely skip that. I don't want you using the auto keyword. Scope. It's a mouthwash. No. Scope of a variable is a part of the program in which the variable can be accessed. A variable cannot be used before it is defined. We're not going to be adding stuff to our program, I don't think, at this point, but scroll up here. You see this variable x here? Could I use that outside of main? Could I come up here and like print out x here? Don't make this change. Cout x indl. No, I can't. Why? Because x is not defined here. X is defined here. The only place x is valid and can be called by that name is between those braces from beginning to end. And as a matter of fact, from where it is defined until the closing brace. So any point after that I can use x, but any point in front of it or any point outside of these braces I can't. We have some other variables, f1 and f2. Until I declare them, I couldn't use them. So I can't do cout f1 indl here. Why? Because it's not defined yet. We have to define them above where they're used, and we have to define them in the same pair of braces in which they're used, or at least in some enclosing braces. So if I wanted that to work, I'd have to move this up above, or I'd have to cut that line and move it down there. That's called the scope. The scope of this variable is from where it's defined all the way down to the closing brace in which it was defined. All the way down here. I can't use it outside of it. I can't use it inside of another function. I can't use it before it. Here's another example. If close, remember our close variable? Don't type this. You can if you want. Int xyz equals wow. No, that's not an int. Is equal to 1. Cout xyz followed by an endl. And then come down here. Could we do something to xyz now? Could we add one to it? xyz plus plus. No, we can't. Why? Because it's not defined anymore. XYZ's scope, its region where it can be used, is between these two braces. It no longer exists by the time you get down here. So that's what scope is. It's what part of the program the variable can be accessed. This can't be, we could print it out here. I mean, we could put that in there and it would work. Or we could move this declaration outside and it would work. But as is, that's not going to work. I'm going to comment this out and say variable can't be accessed. It is out of scope. Meaning XYZ is only available inside the braces in which it is defined. Here's our example. Int main, cout value. Int value is equal to 100. Error, value is not defined. Yeah, this variable was not defined until that line, so we couldn't print it out there. Arithmetic operators. I'm almost sure that we've talked about this stuff already. Except for that one, the weird one. I don't care if you know what a unary operator is. It's just the minus sign. If you say x is equal to minus 5, that minus means take this number and make it negative. Okay, great. Why is it called unary? Because it accepts one operand. You have a minus sign that's followed by a number. That's its operand. An operand is the data on either side of the operator. A binary operator is one that has two operands. Addition, subtraction, multiplication, and division. They all have two operators. So binary operators, binary in this case doesn't mean 0 and 1. It means that it takes two pieces of data. Addition, subtraction, multiplication, division, and modulus are all binary operators. So 1 plus 2, right? A minus B. C times 100. 100 divided by D. 13 modulus 3. Have we talked about that guy yet, modulus?
Yeah.
Good. Don't want to do it again. Alrighty, so these are binary operators, meaning they take two operands. The operands are the values on either side of the operator. An operand can be a literal, it can be a variable, or it can be an expression. What do I mean by that? If you do this, A times B plus C, we have two operators there. We have that one and that one. What are his operands? B and C are his operands. Now we have an asterisk. What are his operands? A and the result of B times C. So that's an entire expression being used as an operand for another operator. The act of combining multiple expressions into larger expressions is known as composition. That's composition right there. Yeah, we could do other things. Never mind. I'm not going to chatter about that. And then there's something known as the ternary operator. Ternary takes three operands, and this is kind of silly. That's not silly, it's useful. I'm going to declare, go back to your code, let's actually use the ternary operator. Let's declare something called temperature, and we're going to set it equal to 200 degrees. And then we're going to declare a string, which is going to have the value hot or cold in it. So string I'm not coming up with a good name for it, so how about S? And so if the temperature is higher than 100 degrees, S is equal to hot. Else, S is equal to cold. That's one way to write it. It's a perfectly good way of writing it. We could have written it in one line, though. I'm going to rewrite it so that it takes one line. S is equal to, and I'm going to use some parentheses here that are not necessary. S is equal to temperature greater than 100, question mark. If so, hot, colon, cold. Now the parentheses aren't necessary. You could take those out. So what the question mark means is this part true? If this part is true, do that. Else, do that. So it's a miniaturized if-else statement. So if temperature is greater than 100, hot gets copied into S. If temperature is not greater than 100, if it's false, then cold gets copied into S. So these two blocks of code are exactly equal. They're exactly the same. Maybe you can see why some programmers lean towards doing it that way. Makes the code more concise. Also makes the code slightly harder to read. So this does the same thing as the if-else above.
Will it work if we keep both of them?
Yeah, it's just going to set it equal to hot or hit equal to cold 2 times in a row.
Quick question. Can you
Yeah.
call a function before it's been assigned, like before it's been read off? Like if you write a function below...
Yes, the question is, can you, do you always have to define your functions before you use them? And the answer is no, you don't. You use what's known as a prototype. And you can stick that prototype in a header file, but I'm going to give you an example of it. Scroll up to the top, above your main, and we're going to do this. Do void howdy int, nothing. Void howdy, parentheses, in parentheses, and then just put a semicolon there rather than our braces. Got that? Now come down here to the bottom and let's create a howdy function. So underneath system pause, underneath the brace, at the very end of the program, void howdy, parentheses, in parentheses. Inside our braces, we're going to do howdy partner, \n, cout, glad to see you. And now is the last thing before our system pause. Insert a call to howdy, like that. And I got build errors, so I have to figure out what I did wrong. Oh, I added a C out that broke it because I was trying to show you that it wouldn't work. And I left it in there, and sure enough, it didn't work. All right. So it did print, howdy, partner, glad to meet you, glad to see you. But if we had not declared this so-called prototype, scroll back up to the top, find that word void howdy with the semicolon, comment it out. Try to build it and run it again, and it won't.
What if it won't build from the beginning?
Well, I'll wander around and I'll help everybody get it compiled in just a minute. Well, we're getting a lot of warnings, but anyways, there's an error. It says identifier not found. And the problem is because I am calling howdy before it is defined. It can't run the howdy function if it doesn't know what it is. Other languages don't do this. They do this a little bit differently. Python and C require you to forward declare your functions, meaning you have to declare your functions before you call them. Java and C# and a whole bunch of other languages do not. But if you don't want to forward declare your function, if you don't want to have, main below a whole bunch of other code, you use prototypes. What the prototype means is, later on there's going to be a function called howdy. It doesn't take any parameters, any arguments. It doesn't return anything, but I'm going to give you the code later. So this is like just defining the header. And then down there somewhere underneath it, or maybe even in another file, you put the actual function declaration. So the answer is yes, you do have to define your functions before you call them, but you can get away with not doing so if you use prototypes. Does that make sense? It'll make more sense the second time we hit it. All right, so who's getting compilation errors that they need help with? Let me wander around and help y'all. In fact, we're real close to being done, aren't we? Why don't we, I don't want to just say stop there. Let's go look at the slides and see what's left to do. Arithmetic operators. We know what addition, subtraction, multiplication, and division and modulus do. Have we talked about PEMDAS? Precedence. I'm looking at you, Olivia. Have we not? Okay. So our rules for in what order things are solved. What if I do this? A is equal to 3 plus 4 times 5. What is A equal to when we're done? Two ways you can interpret this. If you grabbed your $5 calculator and you typed 3 plus 4, enter, that'd say 12. Times 5, enter, it'd say 60. But then if you get a more complex calculator that can accept multiple things in the same line, 3 plus 4 times 5, you type in a whole expression before you hit enter, your TI-30 or something like that, it'll come out with a different answer. The reason why is multiplications are done before addition. And that will sound familiar. Y'all have already done that in elementary school or junior high or high school. So multiplications are higher priority precedence than addition.
We have done this.
We have done it.
I do remember it now.
Alrighty, good. Alright, good deal. So PEMDAS, what's at the top of the ranks? Parentheses. Underneath that, multiplication, division, and modulus. And then lastly, addition and subtraction. So we can skip that slide.
I don't know what you meant by PEMDAS.
Yeah. It's an acronym, a mnemonic that means parentheses, multiplication, division, addition, and subtraction. That's how kids are taught to memorize it. Please excuse my dear Aunt Sally. The missing E is exponents, but we don't have an exponent character in our language. And I know we've talked about this. If you divide two numbers and they're integers, it rounds down. But if you do a division and one of them is not an integer, or both of them is not an integer, it does not round down. So 13 divided by 5, these are both integers. So it rounds down to 2, instead of saying 2 point whatever. 91 divided by 7, instead of equaling 13.345 or whatever it is, it's just 13, because these are both integers. You Python users, remember we had a single slash and we had two slashes. Single slash meant division, two slashes meant integer division or floor division. We don't have that in C++ or Java. We just have slash, and its behavior changes based on whether the operands are both ints or whether one or both of them are floating points. If you give one of them a floating point or both of them floating points, it calculates it exactly and doesn't do any rounding. So 13 divided by 5.0 is now equal to 2.6. And why does that matter? Because if you type in an equation like this, so the volume of a sphere is equal to 4 divided by 3 times pi times radius to the power of radius cubed. Power radius cubed. That is a true statement. Unfortunately, what happens is as it's processing this, it goes 4 divided by 3. Cool, man, these are both integers. I'm going to round it down to 1. No, 4/3 is not supposed to be 1, right? It's supposed to be 1.33333. So this would not give us the right answer unless we change one of them or both of them to floating points. Why 4.0 and 3.0? So it won't calculate 4 divided by 3 as equaling 1. That's far enough. Now I'm happy. Let's go ahead and make a Dropbox. Check our homework situation, how if we need a new assignment yet. Let's do on the 18th. Why don't we wait till Thursday to have our new homework assignment? I actually think that we could do another assignment. Let's, I'm going to show you the next one and I'll upload it later. Refresh your Dropbox. You'll see in class G. Don't know why I put September 12 lecture. So you remember our BMR assignment, or in class, where we were calculating somebody's body mass ratio based on their height and based on their width? No, I'm kidding. Their weight. Instead, we're going to calculate what's known as BMI, basal metabolic. No, that's not true. We calculated BMR. What did we calculate?
BMI, body mass index.
Yeah, we did body mass index, and instead we're going to do BMR, which stands for basal metabolic rate, which is a completely different thing. How many calories your body burns on average in a day. Alrighty. Now I didn't create this when I got this from the last C++ professor, and I keep slowly but surely removing silly stuff out of it. But if it looks silly, just know that I haven't edited enough. Okay, health and fitness software development. In this assignment, you'll write a computer program that asks the user for some information that computes the number of calories that they burn each day. What do we need to know? We need to know their weight in pounds, their height in feet, and their age in years, because as unfair as it is, a 40-year-old person does not burn as many calories as a 20-year-old person, even if everything else is equal, and an activity index. The activity index describes how active you are. If you're a couch potato, it's really low. If you're Michael Phelps and you're swimming 17 hours a day, then it's really high. So go ahead and declare all variables as double. Here's what the activity index means. If you are sedentary, little or no exercise, your activity index is 1.2. If you're lightly active, it's higher. If you're Michael Phelps, then exercising 2 times a day, it's 1.9. So here's the formula. BMR, basal metabolic rate, is equal to, and then it's just equal to all of that, where WT is equal to your weight, HT is equal to your height, and AG is equal to your age. How this is calculated, I don't know. And then, once you have your basal metabolic rate, you multiply that by your activity index to figure out how many calories you burn on a day. So it's 2 calculations in a row, although conceivably you could turn it into 1 calculation. If you're a math guru, you see how you could do that. So, for example, imagine a person who weighs 135 pounds, who's 5 feet tall and is 61 years old. And their activity is sedentary. So their activity index is 1.2. So the BMR value for this is you add all those things up, just according to that formula. And then you get a BMR, and so their calories are equal to the BMR times the activity index. So it's equal to that times 1.2 is equal to they're burning that many calories a day. Note, all calculations are approximate. The weight really should be lean body mass. Okay, give me a break. So I've written this program, and here are the sample runs from it. Your output should, like I said, this is a little bit silly. I have removed a lot of extra stuff from it, but here's the way the program could look when you run it. To advance your health, we will calculate how many calories you burn a day. We will need data on your weight, height, and age, and what kind of activity you do. So that's all just C out stuff, right? There's no input there. Please enter your weight in pounds and press enter. And then you use a C in to store their weight. Please enter your height and feet and press enter. So they type in 10 feet tall or whatever. Please enter your age and years. 37, whatever. And then these are activity indexes for different lifestyles. Please pick the one that's appropriate. And then we describe them all. Desk job, 1.2. Light exercise, 1.4. Moderate, 1.6. Hard exercise, 1.7. Training, super hard, 1.9. Based on this information, what is your activity index? 1.2. And here are the results of our computation. You burn this many calories a day. Thank you for using. And so that's another sample run. They type in different values, right? So go ahead and write that program. What I don't want you to do is just say, what is your activity index, and not give them any other information, right? Because they're not going to know what activity index means. They might type in 1,000, they might type in 0 or whatever. Go ahead, and although it seems tedious, display all this information. You could make your program a little bit cooler. If you have the concept of if-else's nailed in your brain, you could ask them, if you have a desk job, press A. If you do light exercise, press B. If you do moderate exercise, press C. And then you can convert. You know, if they chose A, then make your activity index 1.2. If they chose B, make the activity index 1.4. But you don't have to do that. You can do it exactly as written here, and that's totally cool. Does that make sense? Not terribly hard. You're just asking for like 4 pieces of data: age, weight, height, and then an AI, and then you're running it through that formula. If you get stuck, certainly let me know. Do you have to use functions? Nah. You know, this is real simple. This is actually no more complicated than our I program was, except the formula is more complex.
When will it be due?
A week from today,
Okay.
or a week from yesterday, actually. Midnight on Monday. All right, guys, let's go ahead and stop. If you had syntax errors you need help with, then let me wander around and help you. Let me stop the recording first so that we don't have a machine correction.